Chaos, famously known to give rise to the butterfly effect, can happen only in some cases. The atmosphere of our planet is one of them. But quantum physics isn't. It's a linear theory, and linear theories can't be chaotic. But if we look closely at matter, it's all quantum physics. So how can chaos ever happen? That's a very good question, Sabina. I'm glad you asked, because no one has an answer. I think it's one of the most neglected, if not the most neglected question in the foundations of physics. So neglected that most physicists will tell you it isn't even a question. But good thing you have me to remind them. And today I have a wonderful paper that shines light on what happens in a quantum system instead of proper chaos. Chaos means that small changes in initial conditions lead to vastly different outcomes, like your headline is always just one typo away from disaster. An intuitive way to see why quantum physics can't be chaotic is that chaos requires any small perturbation to become exponentially amplified. But in quantum mechanics, everything is described by a wave function, usually denoted psi, from which we calculate probabilities. And probabilities can't get larger than 1. They can't continue growing indefinitely. Imagine being late with a probability of 3.5. Now, that'd be awkward. So what happens in quantum mechanics is that it might look for some while like chaos sets in, but then eventually it doesn't. It gets washed out by quantum uncertainty. This is a fascinating process which physicists study with a rather simple example. That's a particle, either with or without quantum properties, that's confined in a closed area in 2 dimensions. It gets an initial kick and then bounces off the walls. Whether the motion is chaotic depends on the shape of the boundary. An example that's known to be chaotic is called the stadium, because that's what it looks like, a rounded rectangle. For a point particle, the track of the particle never repeats. If you just wait long enough, it'll get arbitrarily close to any point in the stadium, and this is also a sign of chaos. For a quantum system to resemble this, you'd expect the probability of a quantum particle to smear out evenly across the stadium. But this is not what happens. Instead, what happens is what you see in this animation. A pattern develops. There are paths within the confined space that have a higher probability than others. They're called quantum scars because they look like scars on the classically even probability distribution. Exactly what scars you get depends on both the shape of the confined space and also the initial state. Here, for example, you see what happens for the shape of a heart. These quantum scars have so far been hypothetical, but this is where the new paper comes in. They realized they set up with the stadium in a sheet of graphene. On the sheet they create a boundary with an electric field from an electron scanning microscope. Then they watch how an electron moves around in this confined space. They choose an initial state that should give rise to this infinity-shaped scar which you see in this animation. Without quantum effect, this shape wouldn't exist. And their measurements beautifully confirm the predictions of quantum physics as you see in these images. There is the quantum scar. This result aligns perfectly with an early experiment that found that quantum physics doesn't have a butterfly effect. Now you could say that, well, they just confirmed quantum mechanics. What's the big deal? No one really doubted this in any case. But allow me to try and convince you that this is very interesting for 2 reasons. One is that quantum scars are a new method to guide the transport of electricity and energy in materials, and that could come in very handy for designing miniature electronics. Graphene, which they used in this experiment, is one of the big hopes of the computing industry for new methods to miniaturize microchips, and maybe this'll be the breakthrough for smaller, faster, more efficient devices. The other reason this is interesting is that it's yet another avenue to explore the crossover between the quantum regime and the classical non-quantum regime. And we know that somewhere along that path, the measurement problem of quantum mechanics lurks. Studying phenomena like quantum scars could help us figure out how classical chaos emerges from quantum rules. But wait, I heard someone shout at the back. How can it be that there is no chaos in quantum physics? when I've read papers about quantum chaos. Indeed, physicists do have a notion of chaos in quantum physics, but it's not the same as in non-quantum physics. It's basically a resemblance to real chaos that can survive for some time in a quantum system. So in summary, the great thing about quantum chaos is that it doesn't exist. The new technology I'm most excited about is without doubt nuclear fusion. This is because I think that the growth and prosperity of a civilization is ultimately determined by its energy access. Today I want to tell you about a new nuclear fusion startup in New Zealand that's come up with an idea I've never heard about before, and they just reached their first milestone. Let's have a look. For half a century, nuclear fusion seemed pretty much unachievable, but in the past decade, we've seen startups popping up all around the world with new ideas for how to get it done. There are now more than 40 fusion startups, most of them in the United States, and the total funding exceeds $7 billion. But not all is sunny. Several of these companies made promises that they almost certainly already regret. The UK company First Light Fusion, which is shooting projectiles at nuclear fuel pellets, for example, said in 2019 they'd achieve energy gain by 2024. The American company Commonwealth Fusion, which uses the well-trodden tokamak approach, said in 2021 they'd commercialize their technology by 2025. They've now moved that date to 2027. Most of the nuclear fusion startups say they'll deliver power to the grid before 2035, so the next 10 years will be very interesting. The big challenge for nuclear fusion is that one needs to push small atomic nuclei into each other against the electric repulsion between them. The Sun does that with its enormous pressure created by its own gravitational pull. Here on Earth, the methods that scientists use to create sufficient pressure come in three broad classes. There are those that trap and heat nuclear plasma with magnetic fields, known as magnetic confinement. Then there are those that shoot at fuel pellets, known as inertial confinement. And then there are some which combine both. We talked about all these in a previous episode, but basically it's trap it, zap it, or hope that no one asks exactly how it works. The company which just made headlines is called OpenStar and was founded in 2021 in Wellington. They're a private company that has so far attracted about $12 million in funding. They're using a type of magnetic trap-it design called a dipole fusion reactor. As the name suggests, it works with a magnetic dipole field. This is a very simple field like that of a standard magnet with two poles. In the often used tokamak design, which is what ITER uses, one has a vessel that has the shape of a torus or donut or bagel or whatever your favorite bakery comparison. The plasma must be made to float inside the vessel without touching the walls because it's so incredibly hot. In the dipole fusion reactor, on the other hand, the plasma vessel does not have a hole in the middle. Instead, one levitates a big torus-shaped magnet inside of the vessel. That magnet creates the dipole field. If the magnet is superconducting, it can be strong enough to trap the plasma and heat and compress it, hopefully enough for fusion to set in. The idea was proposed by physicist Akira Hasegawa in the 1980s. MIT then had a small test device which ran from 2004 to 2011, but it was discontinued due to lack of enthusiasm, basically. Like with all other nuclear fusion technologies, the problem is just to get more energy out than one needs to put in. OpenStar is now building on the MIT results and wants to optimize the design to create net energy. The dipole design has several advantages over the tokamak. The biggest advantage is its simplicity, which helps to stabilize some of the turbulences that can occur in nuclear plasma. Turbulence is bad because it can allow the plasma to hit the reactor vessel, which would damage it. Therefore, if it looks like turbulence sets in, the reactor needs to be shut down quickly. This is not a way to efficiently create energy. Turbulence is the biggest headache for magnetic confinement. The dipole design can't entirely avoid it, but the math says that the risk should be much lower, and the MIT results partly confirm this. This is an advantage not just because it's easier to build, but also because it's more efficient, and because it's easier to build, it's less costly. The biggest disadvantage is that one brings in a new instability, which is that the superconducting magnet itself needs to be kept levitating in place. This requires a high-precision control system with active feedback, something that artificial intelligence has now made dramatically simpler. OpenStar now recently announced that they've made a big step forward. They've created and contained a plasma cloud for 20 seconds at around 300,000 degrees Celsius. 20 seconds doesn't sound like much, but for a first test run, that's pretty amazing. Just take my word for it. The last time I tried holding something together for 20 seconds, it was a yoga position and it didn't end well. On their website, the company says that producing energy from fusion is as little as 6 years away. And since it's Christmas, I'll just choose to believe it. After all, the holiday season is all about hope. Hope for peace, hope for clean energy, and hope that this year my mum doesn't burn the turkey. If everything goes according to plan, then by the time this video goes live, I'll be sitting next to a Christmas tree with my family. And since I don't want anyone to fear they'll be missing out if they stay away from YouTube, we'll not run a video for the next 2 days. We'll be back on the 27th with a video about intuitionists' maths. Until then, I wish you happy holidays. Today I have a very ambitious paper from 3 physicists who claim they've solved one of the greatest mysteries of physics: why cats are either dead or alive, but not both. Let's have a look. Schrödinger's famous cat is a thought experiment meant to illustrate the absurd consequences of quantum physics. You see, in the mathematics of quantum physics, everything, let's say a particle, is described by a wave function, usually denoted psi. Depending on just what the particle's doing, its wave function will be different. We could have a wave function describing the particle going left and one describing it going right. The odd thing is now that in quantum mechanics, once you have that, the mathematics also allows for a particle that's the sum of going left and going right. This is called a superposition. And what even is that? Now you could say that, well, doesn't really matter, because these odd things only happen in the tiny quantum range where we don't see it, so who cares? But not so fast, Schrödinger said, because we can amplify these superpositions from the small to the large. He said, let's suppose we have an atom that's in a superposition of decayed and not decayed. If it's decayed, then that decay triggers the release of some toxic substance, which kills a cat. So now the cat must be both dead and alive. But why do we never observe this? In the many-worlds interpretation of quantum mechanics, which the authors of the new paper use, the problem presents itself somewhat differently. In that interpretation, the cat's dead in one universe and alive in another one. The problem is then why there isn't any one universe in which the cat is both dead and alive. Who or what selects what's allowed in a universe? The quantum vet? Probably not. Physicists have tried to get rid of this problem by blaming a process called decoherence. Decoherence is the loss of coherence, a phenomenon that you can observe in your local pub past 8 p.m, but that more importantly scrambles up quantum effects so that they become impossible to measure. This scrambling is caused by interactions with the environment that might be air molecules or just quanta of light, the photons. Or so they say, because that doesn't properly work. Decoherence basically tells you which states are still allowed after quantum effects have been destroyed. The trouble is, though, that the answer you get depends on what assumptions you make about the environment. If you take an environment like the one we find ourselves in, what with air and light and so on, then cats are either dead or alive. Hooray! Hooray! But just mathematically, there are environments in which dead and alive is an allowed result of decoherence. What this means is that decoherence just turns the question of why the cat is never both dead and alive into the question of why the environment of the cat is the way that it is, which we don't have an answer to either. So decoherence just moves the problem from the cat into the environment of the cat, which really explains a lot about cats, doesn't it? And this is where the new paper becomes relevant, because the authors say that they've solved this problem. They say they've found a way in which a system that's combined of a quantum state, that would be the dead and alive cat, and an arbitrary environment unambiguously selects the states that we actually observe. The way that they go about this is with a little mathematical model that you see sketched in this figure. They have two big systems that you can think of as the cat being dead and the cat being alive. They could also be in the state of the cat being dead and alive, which is what you don't want to happen. These two states have some interaction between them. That's this red region that they describe by using random matrices. Their results are what you see in this figure, where the horizontal lines are the classical states, so the dead and alive cat, basically. You can see that for a variety of initial states, the entire system always ends up where it's supposed to, dead or alive, but if you wait long enough, nothing in between. In the many worlds interpretation, this explains why we find ourselves only in universes where cats are either dead or alive. Problem solved? It looks like it. But, I'm pretty sure that the original problem, that there is always an environment that gives rise to a dead and alive cat, is a mathematical truism. If that doesn't happen in their setup, it means that their result depends on the assumptions they've made about the system. Unfortunately, the paper didn't contain enough details for me to check this. So I think this is a very interesting result if it's correct, because it would solve a huge problem. But I'm very skeptical that it's indeed correct, and I doubt that this is the last we'll hear about dead and alive cats, so don't forget to subscribe. Elon Musk wants to build a colony on Mars, but he's not the only one with ambitious space plans. His biggest competitor, Jeff Bezos, is catching up. He's just completed his new reusable rocket, and his space plans are, if anything, even wilder than Elon's. Jeff Bezos is probably best known as the founder of Amazon, but in 2000 he also founded Blue Origin, a private spaceflight company. It so far made headlines primarily for offering brief space trips for rich people, but Bezos' vision is far grander. He wants to build cities in orbit around Earth. Blue Origin space trips are made with a suborbital vehicle. This means that it doesn't have enough thrust to fly off into outer space. It goes up, lingers at the edge of space, and then falls back down. If you have a few $100,000 to spare, you can book a trip and enjoy a few minutes of weightlessness, views from space, and the warm feeling that you just made the second richest man in the world a bit richer. But Bezos doesn't want to become the king of space tourism. He wants to become the king of space. To that end, his company has been working on a reusable rocket that can reach space proper and, like Elon's rockets, put things into orbit around Earth. Bezos' new rocket is called New Glenn, is 98 meters high and designed to carry up to 45 metric tons to low Earth orbit. In terms of payload, that puts it between SpaceX's smaller rocket, the Falcon 9, and the bigger one, the Falcon Heavy. At the moment, Elon Musk is well ahead of Bezos. While SpaceX has been launching rockets for more than a decade already, New Glenn has yet to fly. It was originally set to launch in 2020, but faced repeated delays. Bezos hired a new CEO last year, and construction on the rocket seems finally completed. The company is now waiting for approval for its first test flight. One of the major differences between the New Glenn rocket and the Falcon rockets that probably contributed to the delay is that the New Glenn uses methane as fuel, whereas the Falcon rockets use kerosene. At least theoretically, methane is better at converting mass into thrust, and it has a cleaner combustion. In practice, I guess we'll have to wait how well it blows up. But the New Glenn rocket is just a small first step of Jeff Bezos' larger plan. He wants humans to populate the orbits around Earth. In his plans, he draws inspiration from physicist Gerard O'Neill, who proposed rotating cylinders whose centripetal force would create some artificial gravity, and that could host millions of people.
What O'Neill and his students came up with was the idea of manufactured worlds, rotated to create artificial gravity with centrifugal force. These are very large structures, miles on end, and they hold 1 million people or more each. Let's take a look at what they might look like inside. High-speed transport, agricultural areas.
Bezos doesn't just want to do this for fun. His ultimate goal is to move all heavy industry into space. Resources would be mined from the moon or asteroids, and energy-intensive work would be performed in orbit powered by huge solar arrays. That way, we would not need that much energy down on Earth, and we would also have less pollution.
Who knows how many years it will take, but we can set up the preconditions where the next generation or the generation after that will be able to move polluting industry off Earth. And then this planet will be maintained as it should be, and can kind of be, you can sort of think of it as zoned residential and light industry. And if you want to use large amounts of energy and large amounts of pollutants and so on, you go do that off Earth.
To get that done, the costs of space flight have to dramatically drop, and the travel has to become more convenient. And that is, in my understanding, why Bezos is working on this space tourism vehicle and reusable rockets. To me, Bezos' vision makes considerably more sense than Musk's. Musk wants to build a colony of about 1 million people on Mars, a trip that takes 7 to 9 months one way. By his own admission, it makes no commercial sense. Bezos' plan, on the other hand, does make commercial sense. Not now, but one day it will. Indeed, I think he's right that this is going to happen one way or another. If humans survive for sufficiently long, we'll mine resources in space. And once we start doing that, it makes sense to also move manufacturing to space. Bezos and Musk are not the only ones in this business, of course. There are a couple of smaller companies which also work on reusable rockets, and China has some too. In the past decade, we've also seen several asteroid mining startups pop up. They mostly died because at the moment the costs and difficulties of space travel are still way too high. If you need more evidence that the time hasn't yet come for this business, I talked about it previously, and it was one of my worst performing videos ever. So why am I talking about this again? Well, YouTube is kind of like space travel. It's hard to reach escape velocity. Thanks for watching. See you tomorrow.